Welcome back everyone. We're going to look at the first video in what's called the first fundamental theorem of calculus, and we're going to look at a little bit of background. It's going to be pretty brief, and the pros and cons of using rectangular strips in this. I've read what we're going to do as the second major problem of calculus, and from a book by a man named Howard Anton, a very prolific mathematical author, mainly for university textbooks, and I own one of these textbooks, actually more than one. This page is in one of the calculus books he wrote, and we're looking at there's four major classes of problems linked to calculus, and we've looked at some in other videos, for example the first one, but this video talks about a particularly significant one that baffled early mathematicians: the area of a region, especially complex areas. And that's what we're going to focus on today. This is quite a significant one. This video won't formally introduce the first fundamental theorem of calculus, but it's the beginning of the journey. And from that same Howard Anton textbook, basically the second major problem of calculus can be phrased as such, quoting from the book there, the Calculus 4th edition textbook: given given a function f that is continuous and non-negative over an interval from a to b, find the area between the graph f, that's the line, and the interval on the x-axis. So basically it's the area, we say it's the area under a curve, but really it's the area between the graph's line and the x-axis for a given interval. Okay, and we're keeping it simple at this stage. With the graph, we're looking at where the graph remains above the x-axis. Okay. Now, when starting out on trying to work this through, it might be reasonable to use approximation method. Okay, so a simple shape, you'd have to agree, is a rectangle. So we'll start with a nice simple function, one that you know very well, y equals x squared. Let's say we want to know the area under the curve between the interval 2 and 6. Okay, so it's the area of the region bounded by the curve itself and the x-axis with ordinate lines x equals 2 and x equals 6. That's the interval. And as you can see, it's not a straight line. As you know, it's a parabola, and yeah, that involves some complexity because the gradient's always changing. So we know that by using rectangles, we're not ever going to get the exact answer, but perhaps it's a reasonably good estimate. Who knows? We can see a drawing there of what's called the left endpoint method, is what we're going to look at first, or sometimes it's called left-hand rectangles for short. You can see the blue strips. We call those rectangle strips, by the way. Those blue strips are meant to mimic the area collectively. All four of them are meant to mimic the area under the true area under the curve there. So it's going to be the sum of four rectangles in such a case. Who said to use four strips? Nobody. But it's some reasonable place to start, perhaps. We can already see that there's some gaps there between the top of the strip and the actual curve. So that'll be interesting, won't it? So essentially, the height of each rectangle is determined by the left top corner of each of the rectangles. So the curve touches the left-hand side. So left, it's what's called the left endpoint. So, you know, the area of a rectangle is length by width. So let's employ that basic premise, and let's say A, where that's the estimated area. So we need to look at, well, the first height is determined by the ordinate line x equals 2. So we've also got a constant strip width, which is what we need. Okay, and that's a strip width of 1, as you can see. So it's going to be f of 2 times 1 for the first rectangle. Then we have to add the area of the second rectangle, and so on. Okay, so these are simple calculations. I've dropped the times 1 on the second line, and we just substitute the values for x into the given function, y equals x squared. So we have 2 squared plus 3 squared plus 4 squared plus 5 squared. That area is 54 units squared. Okay, looking closely at the diagram, that's going to be, in fact, I need to start looking at an alternate notation. So let's call this A asterisk. I've got an idea. Look, okay, the asterisk on the left-hand side means left endpoint method estimate. Okay, so we can see this is going to actually be less than the true area, because look at the white gaps. I mean, come on. So that's going to underread. So that's going to be less than, let's call A the true area. Okay. Okay. We look at the other method I said we're going to use, and that's the right endpoint method. Right endpoint method, and better neaten that up. So we can see that we've got different ordinate lines. So there we're looking at the right endpoint of each rectangular strip touching. Okay, so look at the contrast between that and the one above it. You can see the result's going to be different. You can just see straight up, can't you, visually? Because we have different ordinate lines. Look, we're not using f of 2. Last time we used f of 2 in the previous one. On the right hand endpoint with the asterisk on the right, the estimate's going to be based on different inputs. So we've got the first one. See, we've got 3, 4, 5 there. So the first one's going to be f of 3. I'm not going to go times 1 because all the strips are 1 unit wide. So f of 3 plus f of 4. This will give you the vertical height of each of the strips times by 1 the width, which I'm not showing because I don't need to. And you can't make me. So basically we have these inputs here, so up to f of 6, which is different to last time. Okay, and we have 3 squared plus 4 squared plus 5 squared plus 6 squared. That comes to 86 units squared. Let's analyze the graph visually. That's going to overread, okay, because if we look at the original shape and its area under the curve there, we've got bits of area popping through the top of it. Alright, so that's going to overread. So that is going to be greater than the true area. Okay, but is it a worthy estimate? Don't know yet. If we went from our 4 strips to, let's say, twice as many, 8 strips, well, we could try that. We could try it for left-hand strips and right-hand strips. The main difference here is that we don't have integer values going into necessarily into the function, but that's no hassle. It's a continuous function. So the ordinate lines are twice as many, but they're only half the width. Okay, so there's 8 lines. The left-hand ordinates are listed here, 2, 2.5, etc. Up to actually 5.56 is actually not a left-hand ordinate line. On the right hand, it'll start from 2 and go up to 6 again. Now, because there's twice as the interval's the same, the area is the same, but there's twice as many strips, so they're half as wide. So the strip width is 0.5. Okay, so again, this one will start at 2.5 and then it'll terminate at 6. So just makes the calculation longer, and you have non-integer values put into the function. Now I've written that out, but that's not complete yet, because we can't just do what we did up here, right here, because the strip, remember the strip widths were 1, they're 0.5 now. Notice how there is a factor of 1, or the factor of this constant strip width with every term. Well, I can just factorize that out the front, but it's going to be a half for the one we're working on, because I said the strip width is a half. It's a rectangle, so it's height times width. So if the strip width of a half, quick ways to factorize or group it all together, multiply it by 0.5 and shut the gate there, then we can enter that in, and that's 61.5 units squared. Okay, we can see again it's going to underread, so that's still going to be less than the true area. Without showing the calculations, I'll show the result now for right right end method, right endpoint. So the right endpoint method is 77.5 units squared, and by observation we can see that's going to be over the true area. Now, going through all the bother of stripping things down into narrower but more strips, that's more work. Does it at least yield a better estimate? Well, the answer is yes, it does, and it can be proven mathematically, or it can be demonstrated visually, which is what I'm going to do in this video on considering the scope of the course that this video is aligned to. So I'm using an app from GeoGebra, and there's the author of it there. Okay, and I don't know if you can see, but we've got a function. The function is called f of x equals 4 take x squared. So something different. Deliberately chose this one because it's actually it's falling in that interval we were looking at before. So 2 through to 6, it's falling. Okay, you can see where my cursor is going down there, which, well, maybe that's different. We've got differences too here. We've got an interval which goes into the negatives for x as well. So I'm just seeing, just making some differences here. And we're going to see also increasing the number of intervals. Now I've got it set at 12. That's way more than we had n equals 4 and n equals 8 on the previous one. So we're actually looking at a whole bunch of things here. A different function. We're looking at going into the negatives as well as the positives with the interval, and the number of strips is going to be changed as well. And we're going to look at the effect on all of these things together, so stay tuned. So what I won't show here is the calculations, okay, because the app will do that. So what does it look like? Left-hand strips? Let's check that out. So there's for left-hand strips, and it also calculates the area for us, about 10.59 units. And we can see, well, does it overread or underread? Well, look where we are. If we're in the rising interval, okay, you can see that it behaves differently to when the interval's falling. So this is rising, the increasing function in that interval, and a decreasing function is going down in that interval. And a left-hand strip method, left-hand endpoint method, will underread in rising interval, and it'll overread in a falling interval. You should probably note that. Okay, so for a continuous function that's rising, left-hand sums method, left-hand endpoints method will underread when it's increasing, and in a decreasing interval it will overread. What about the right-hand method? Okay, it's the opposite. So as we have an increasing function or an increasing interval in a function, it overreads, and with the decreasing interval it underreads. Okay, you can see it's a game of opposites there. Okay, the other thing we're going to check out, well, when a is -2, it doesn't make any difference at all in the calculations. You simply do the calculations exactly the same way. You sub, depending on whether you're using left or right rectangles, you sub the values for x into the function, and you still calculate it the way. So it works fine. It doesn't matter whether x is negative or positive for any part of an interval. What about the all-important number of strips? It's already at 12. Well, this is an intuitive way. This is not a proof, but look what happens. Actually, let's go back the other way. Let's be really crude. Two intervals. Now that blue, or the red, there's no way that they're a good approximation. Alright? They're lousy. So it says it's 8. Nah. Alright, that's pretty obvious. That's no good. So 2 strips, very crude. Let's go to 4. Alright, and that's still pretty crude. We had 4 before, remember? Alright, what if I increase it now to 8? That's better, but it's still a bit woolly, isn't it? Doesn't matter which one you use. They're both giving the same calculation, 10.5 and 10.5. Okay, let's ramp this up, and I'll just turn one of them off. Now, if we could be there for a long time, or use a spreadsheet or something, we could find that ultimately, when we have a lot of strips, we get an area that comes very close to the true area underneath the curve. Okay, we've got lots and lots of strips that are all incorrect. That they're not fully aligned with the curve, but they get closer and closer. So there's lots and lots of tiny errors, and the overall error is lower. And it doesn't matter which, for this particular curve, because of the symmetry, it doesn't matter whether you use left or right hand sums. So the increasing number of strips gives you a better and better estimate. Now, the wonderful thing about mathematics is that we can take the limit of that, that might appear in the next video perhaps, and we can come up with a true area with a zero error. So in this video we found a few things. We found out those two facts there about the increasing and decreasing intervals and the overreading and the underreading. Okay, that's not an F, that's an arrow, I'm sorry. We found out increasing the number of strips provides us with what's likely to be a better estimate. And we're going to take that to the limit, literally, in the next video, alright? And it doesn't matter about whether the interval has negative x values or not. Okay, so that's coming up. And there are other methods too. There's another video I've done on the trapezoidal rule, which doesn't have rectangular. Doesn't have rectangular strips. It doesn't have a flat top. It actually has a trapezium there. And that's in another video of mine that you'll find. So that's trapezoidal rule. That can be better sometimes, and one that can be even better sometimes is Simpson's rule. And I've got a video on that which uses strips with parabolic tops on the top. Okay, see ya.